Okay, on to question 3, which is an amplitude modulation question. So if you see a graph like this, the first thing you should do is draw the envelope on top of that AM signal because you're going to need it later on for the rest of the question. Now you can't just do that, you got to be able to do the rest of it, of course, but it's a good place to start is to draw that envelope. So first thing it asks is what's the amplitude of the unmodulated carrier and the message signal Vm? So we're going to use the two equations that we have for this, which is Vm equals Vmax minus Vmin over 2. And then Vc equals Vmax plus Vmin over 2. Right? These are equations you should 100% have on your cheat sheet in case you need them. And so what we're doing here then is Vmax is the highest point on the graph. So that's going to be 3 volts is Vmax. Vmin is the lowest point on the envelope here, right? So highest point on the envelope, lowest point on the envelope, and this is the above 0 envelope that we're looking at. So 1 volt is Vmin, and then we just plug and chug into this equation. So Vm is 3 minus 1 over 2 equals 1 volt. Vc equals 3 plus 1 over 2, and that's 2 volts. So that's it for the first part, is just really understanding those two equations and how to get it from the graph. So these are the amplitude values. Next, we're looking for the frequency values. So for frequency, we're going to measure peak to peak, and we can sort of find where it looks like the peaks are. I'm going to go with these 2 points here roughly, and we're going to measure that distance, and that's going to be Tm, right? That's the modulated thing. That's the thing we're like trying to represent with this faster wave that's here. And then for Tc and or Fc, we need to find 2 points on the graph that we need peak to peak of the faster wave. I'm going to use these two here because they look nice and close to each other. So this is going to be Tc. We're just really looking for 2 points, any 2 points on this faster wave. I'm choosing these because this one's at 1 and this one's at 0.5, right? So it's just easier to do the math for this. And so we've got Tc equals 1 minus 0.5, and this is ms. So it should be 0.5 ms roughly. And then we're going to do Fc equals 1 over Tc, right? 1 over the period is the frequency. So 1 over 0.5 ms is going to be, this should come out to 2 kilohertz, which makes sense, half a millisecond. It happens 2,000 times per second then. And then we're doing the same thing for Fm. So Tm is going to be roughly, and this may not come out to exactly what they have on the sheet here, but roughly like 7.5 ms minus 2 ms. And so that would be, I would have 5.5 ms. I think that's not quite what they got whenever they did this for the practice exam. But again, as long as you show your work for this and sort of show where you sampled, you should get credit for it. So we'd have 1 over 5.5 ms, which I think comes out to something slightly different, but on the practice exam, they give you 200 hertz. If we actually push this through, let me see with the calculator real quick, what I should have gotten. 5.5 times 10 to the negative 3 is going to be 181. So 181 hertz is what I got. But again, as long as you sort of show what you did here and show that you picked these values, this is how you get it, is measuring the envelopes period and then converting that to frequency, measuring the carriers period and then converting that to frequency. So then what's the mathematical equation for the amplitude modulated signal VAMT? So we've got VM, we've got VC. I'm going to use a slightly different format for this than what the exam solution used. So I'm going to say this is VC sine 2 pi FCT plus VM over 2 sine 2 pi FC minus FMT plus VM over 2 sine of 2 pi FC plus FMT, right? So this is our lower sideband. This is our upper sideband. is what we're showing here, and this is our carrier frequency, right? So again, this is a good equation to have locked and loaded on your equation sheet just in case you need it for this type of problem. So then VAMT, we're just plugging in values, right? So VC, 2 volts, sine 2 pi, FC, we got here, 2 kilohertz, T, plus VM over 2 is 1 volt over 2, so 0.5 volts, sine 2 pi, FC minus FM, so we'll use the 200 here just to make this easier, is going to be 1.8 kilohertz, T, plus 0.5, again, this is the VM divided by 2, so 1 volt divided by 2, right? That's what we're plugging in there. Sine of 2 pi, FC plus FM, we're going to use 2.2 kilohertz, T. So that's roughly what we should get there. And again, it's really just plug and play the numbers into the equation. So part D then, draw the AM signal in the frequency domain in the graph below. So we've already got our values, right? And this is just kind of check your understanding of how the frequency domain works. So we've got our voltages and our frequencies for all of the parts that we need to put on the graph, right? So we just need a line for each of these that matches what we've got in the equation. So we need a 2 volt at 2 kilohertz. So 2 volts is here, 2 kilohertz is here, so we need one spike at that point, right? This is our FC. We need another one at 0.5 at 1.8, so we need our FC minus FM. That's our FLSB, our lower sideband frequency, and then a 0.5 at 2.2 kilohertz. That's FC plus FM, or FUSB, upper sideband. And again, these points are like at VM over 2 and VC, just in case we ask you to do it the other way around, right, and translate it back to like the original signal, right? We have to remember that that's what we're showing here is the unedited carrier amplitude, the unedited carrier frequency, and then the sort of sideband frequencies for the modulated signal, and the halved amplitude for the modulated signal. So that's it.